Okay, this is Chapter 4, Section 1, and this is Part 2, Section 1. And this goes out to Ellen. Ellen, you talk too much. Anyways, combining forces. When we combine two forces in the same direction, basically we can replace them with a vector that is of equal length of their combined lengths. If they point in opposite directions, then we're going to look for the difference of the two vectors. Anyways, we're going to call this new sum of vectors, calls this the net force. No net force means that the object's not moving, but a net force is going to talk to acceleration. If we want to look at acceleration, we're going to look at this figure right here. And we have a horizontal force being observed on an object. We try to reduce any complication by using a smooth table, and we use a cart that has wheels, so basically no friction forces in here. And we're going to exert a constant force. This little thing that they're holding right there, this is a spring scale, similar to the one you saw me using in class. And so you're going to pull on the spring scale so that it's registering a certain number. The velocity of the cart then is measured, and we're going to go ahead and plot a couple of different graphs with that. One of the graphs we want to do is an acceleration versus force. Obviously, it makes a lot of sense that if you increase the force, if you pull harder, the acceleration is going to increase as well. If you hold the force constant, then the acceleration is going to be a constant. That doesn't mean the velocity is constant. The velocity is going to increase, but if you hold the force constant, then the acceleration is constant. If you apply greater force, you're going to get a greater acceleration. The data indicates that a constant force, there's a constant acceleration of the object. And we can make an equation that says y is equal to k, where k is some kind of constant that we're going to use in the equation, x plus b. It makes sense that the y-intercept is 0. If you don't have any force, you don't have any acceleration. So the y-intercept is going to be a 0, and we simply get y is equal to kx. Now, what happens if we change the mass of the thing being pulled? Let's say instead of one cart, there's two carts. It's going to go faster or slower. Well, it's going to go slower. So if we have a velocity graph, time, the slope is indicating of a velocity versus time graph indicating acceleration. If we have more things that we're trying to pull, more carts, then the acceleration is going to be less and less and less. You're not going to be able to accelerate as quickly. So what's the physical meaning then? If we're looking at an acceleration versus force, that original graph, acceleration versus force, what does the slope mean? We really could say that the slope, it can be related to the mass of what is being pulled, and so we're going to represent that with a mass in the bottom. If we double the mass, the slope is cut in half. If we triple the mass, in other words 3 carts, the slope is cut to 1/3. Again, if we plot these things of the force versus acceleration for 1, 2, and 3 carts, indicates that we're going to have with the same amount of force applied, that the acceleration is going to be less and less and less as they have more and more carts. It means that the number of carts is increased, the force needed to produce the acceleration is decreased. The slope of the line then depends on the number of carts, so the slope of the line really then is related to the total mass. So if k, the slope of the line, is related to the mass in an inverse relationship, 1 over the mass, then the acceleration is going to be the force divided by the mass. Rise over run. Rise here is the acceleration, run is the force, is equal to m. We'll switch it around, or to give us a slope, so we could switch it around to say the acceleration then and the mass are reversed. Anyways, finally we get the equation of force is equal to mass times acceleration. That formula tells us if you double the force, then you double the acceleration. If F goes up by a factor of 2, then A has to go up by a factor of 2. If you apply the same force to different objects, the one with the most mass will have the smallest acceleration. 1 unit of force then we're going to define as a Newton. And if you accelerate 1 kilogram by 1 meter per second, 1 kilogram, 1 meter per second, we're going to call that a Newton. And that's the unit we're going to use for force. This is basically Newton's second law. They're writing it as force is equal to, or the acceleration is equal to force divided by mass. Most of the time you're going to see it written as force is equal to mass times acceleration. And we're going to go ahead and apply it here in a little story. We have a dog that weighs 0.3 kilograms, and we have two children that are pulling on it. Sarah, and I don't even know how to pronounce that one. Sarah's pulling horizontally with 12, and Annie here is pulling with Sarah's pulling with a force of 10. Annie is pulling with a force of 11. We diagram it out. We draw a circle around the dog, our object of interest, and we draw a force diagram, or free body diagram. So the dot represents the dog, and the two vectors are pulling on each direction. Obviously, the Annie's vector is going to be a little bit longer than Sarah's vector. If we want to solve for the unknown, we have F2 is 11 and F1 is 10. Can we figure out the acceleration? Well, if the acceleration is equal to the net force over the mass, then we need to figure out the net force. 11 minus 10 is 1, and the mass is at 0.3. So 11 minus 10 is 1, 0.3. We can get an acceleration of 3.3 meters per second squared. And it seems to make sense. Let's go on then. What's the motion of an object with no net force on it? Well, Newton's second law says that if there is zero net force, then there's zero acceleration. If there's zero acceleration, then the velocity is not changing. If you're in motion, you're staying in motion. If you're stopped, you're stopped, but your velocity does not change. Stationary objects with no net force will stay at rest. Okay, but what about a ball rolling along? Depends on the surface. A thick carpet with more force than a smooth surface of the bowling alley. So the ball will stop rolling on the carpet quicker than it will in a bowling alley. Galileo did many experiments and concluded that in the ideal case of zero resistance, horizontal motion would never stop. Kind of a precursor to Newton's laws. Galileo was the first to recognize the general principle of motion must be found by extrapolating experiments. He basically tried to come up with an ideal case, and the closer he got to the ideal, the better it looked. In the absence of a net force, the motion or lack thereof of both the moving object and a stationary object continues as it was. Newton recognized this, and Newton then basically said an object in motion that is at rest will tend to stay at rest, an object that is moving will continue to move in a straight line at a constant speed if and only if the net force acting on the object is zero. In other words, if there's no net force. And we're going to call that Newton's first law. The first law is also referred to as the law of inertia. Inertia then is defined as the tendency of an object to resist change, either staying in motion or staying at rest. An object at rest will tend to stay at rest. If in motion, it will tend to move in motion. Forces that are result in an interaction of two objects. Remember, we have to have an object, and then we have to have an actor causing the force. So inertia cannot be a force. Inertia is not a force, it's just a tendency. If the net force is zero, then we say that the object is in equilibrium. Equilibrium means that if the velocity is not changing. Newton's first law then identifies a net force as something that disturbs the state of equilibrium. Thus, if there is no net force acting on an object, the object does not experience a change in speed or direction. Okay, so if you're wondering, we do have some forces that we're going to be talking about. Friction forces, I think you're pretty much familiar with. It's tendency of something in contact to slow something down, tends to act in the opposite direction of the motion. Normal force, I'm going to go into the normal force a little bit more in class, but normal force is basically when a surface pushes on an object. Spring force is, of course, the spring is moving the stuff down. It basically is opposite the displacement of the spring. So if you pull on a spring, it's going to try to move the object back in the opposite direction. Tension forces, we do a lot with tension forces. You guys diagram some today in class. Thrust, this is more like with rockets and so on. This is a little bit more tricky. We'll get into this. And then the force of gravity is going to be referred to as Fg, which is basically weight. And that's it.